We're going to begin looking at solving systems of equations. And so the first way of solving a system of equations by graphing. A system of equations is when you have two or more equations and you're using the same variables represented in the same thing at the same time. And so a solution to that system is an xy pair that satisfies each of the equations you're working for. So one way to find that is to look at the graphs of the equations, and where they intersect would be a solution to that system. The reason why is this intersection has to satisfy each equation, because that's what it means to have a point on the graph itself. So since that point would be on both graphs, or however many graphs you're working with, then that would have to be an xy pair that satisfies those. So we're going to look at some classifications of types of systems you can have. So let's say we had a line going down and to the right, and another line going up and to the right, and these cross at some spot. We call that system independent, and it has one solution, that point where they cross at. If you have a line, let's say going in this direction, and a second line going in the same direction, then we say the system is inconsistent. There are no solutions to that. There's no crossing. These two lines are parallel, and so they don't meet each other. A third type of system you can have with lines is you can have a line, and then you can have a second line right on top of the first line. In that case, you have a dependent system, and there is an infinite number of solutions. Now, one of the places where students sometimes get confused is with the idea of independent and inconsistent. They sometimes get those names mixed up. And so let me try to explain those terms a little bit more detail and give you some kind of real world examples to help you understand the difference between an independent system and an inconsistent system. So independent means each aspect is acting on its own, and it's not really looking at what is happening with the other things involved. So an example of this might be if you have a student O, how they do on a test is independent of how a different student P does on the same test. So it's possible that both of these students could get A's. That is a possibility. Or maybe one of them gets an A and one of them gets a C. Their performance is independent of each other. So if they both got A's, that would be like, you think about like the two graphs meeting. That's a spot where they both, match. But, on other tests, they're going to maybe score differently. So how they perform is independent of each other. That doesn't mean there aren't situations where they match. It just means that is just a coincidence. It's not a causation situation. Compare that to inconsistent. Inconsistent is when two things can't happen at the same time. It's impossible for them to happen at the same time. You sometimes hear this called they are mutually exclusive. So, for example, a single student can't get an A on the test and also get a grade of C on that same very test. The same student can't get those two different grades. We're not talking about retests or anything like that. I'm just saying the very first time they took that test, they either got an A or maybe they got a C, but they couldn't have gotten both. You can't get an AC. So that's an idea of inconsistent. You either are on one path or you're on a different path, and never do those two paths meet. A dependent would be when you describe two things that go together. So let's say we were looking at the relationship between studying and grades. So you might say something like a student's grade on a test is dependent upon the amount of studying they do. If they do a lot of studying, they get higher grades. If they do very little studying, they get lower grades. So studying and grades, those are two things that go together. So dependent is looking at that that kind of situation where two things match up and they travel in the same path. Excuse me. So if we go back to this again, independent, just look at the two lines. They're just doing their own thing. Yeah, at some point they cross each other's path, but then they keep going in their own different directions. Inconsistent, they never cross paths. They never happen at the same moment, ever. And then dependent is when two things are going together all the time. So you have these two lines right on top of each other. All right, so we might have a situation like this. We're given a graph, it's already drawn for us, and we're just asked to identify what the solution is. And what we're looking for is, where do these two lines cross? And so I'm looking at this point right here, and this point is at 2, 3. So that is the solution to the system. Now, most of the time, though, you're not going to be given the graph. You're going to actually have to generate the graph yourself. So let's look at some example problems of that. So let's say we wanted to solve this system of equations. Now, you could, do intercepts and things of that nature, but, let's go ahead and solve these in the y equals mx plus b format and use that to graph. So I'm going to take this first equation, 3x minus 2y equals -8, and put it in that slope-intercept form. So subtract the 3x from both sides. And then I want to get rid of the -2 on the y, so I'm going to divide everybody by that coefficient of -2. And that gives me y equals positive 3/2 x plus 4. And then I'm going to do, pretty much the same thing with the second equation. So I'm going to take the 2x plus y equals -3, subtract the 2x from both sides, and there it is. It's already in that format. And now I'm ready to just start doing some graphing. So I go to, I want to graph these in different colors, so I'm just going to go ahead and make this second one orange, just to clarify which line is which, but you don't necessarily have to do that when you draw the graphs yourself. I'm going to go to graph this first line. Y equals 3/2 x plus 4, y-intercept of 4, slope is 3/2, up 3 and over 2. That's going to take me off my little grid here, so maybe I want to backtrack. So if you think about it, if I go up 3 and over 2, to go the other way, I would go down 3 and back 2, and I could do that again, down 3 and back 2. Remember, I'm looking for where they meet, so the more verified locations I have, the better it's going to be. And so if I draw a line through those points, I get that first line there. And now I'm going to draw the second line. So 0, -3, that's this y-intercept. Slope is -2 or -2 over 1, so down 2, 1 to the right. And it looks like, oh no, these lines are going to spread out. But again, if I look to the left, I see they're going to meet each other. So if I back up, I went down 2 and 1 right, so if I go up 2 and 1 left, I get that point. Up 2 and 1 left, hey, there we go, up 2 and 1 left, up 2 and 1 left, I draw that line, and I see these meet at the point -2, 1. Now, sometimes students, instead of writing the answer as an ordered pair, which is what you should be doing in this case, they sometimes want to just say x equals -2 and y equals 1. And let me see if I can explain why that is not the way you want to write this answer. So let's say I do that. X equals -2, y equals 1. The problem there is, this is not an answer. This is actually a brand new system of equations. And that system of equations is, there is a vertical line at x equals -2, so 2 units to the left, and a horizontal line at y equals 1. So what you're saying here is, where these two lines meet is the same as the problem I just did, but you haven't, if you say it in this fashion, x equals -2 and y equals 1, you haven't actually stated the solution yet. So you need to write that answer as an ordered pair, -2, 1. So do not write it as x equals -2 and y equals 1. All you're saying is, yeah, there's another system that has the same answer, but you haven't actually stated what that answer is. Alright, let's do one more example. Let's say I want to solve this system. So notice the first equation is already in the y equals mx plus b format. So let me get that second equation in that format. So subtract 3x from both sides, divide both sides by -4, so I get y by itself, and that'll give me y equals positive 3/4 x minus 3. And again, I'm going to change this to a different color to make it easier to see which line I'm graphing. So again, I'm going to go back up to the original problems, and I'm going to use that y equals 3/4 x minus 2, start at -2, rise 3, go to the right 4, and again, maybe I want to backtrack, down 3, back 4, and I draw my line there. And now I go to this one, and I go, okay, I start at -3, and I'm going to go up 3 and 4 to the right, And if I want to backtrack down 3, 4 to the left, and what I see is these lines don't meet. And if I look at the slopes, I see, oh, they have the same slope, but their b values are different. These are parallel lines. And now, even if you knew that before graphing it, you still need to draw the graphs when it's asked you to solve these using graphing. So if it just said solve it, you could have said the system is inconsistent as soon as you notice that they're parallel. But in this case, we still want you to graph it just to get more practice graphing and to show that they are in fact parallel. Right, so that's how you do that. You can have a system that's dependent and you draw two lines right on top of each other. If it's an independent system, we usually just state, unless we're specifically asked to identify the type of system it is, we usually just state what the solution is. We don't say it's independent. Right, so that's how you solve systems of equations.